main objective of this program is to represent a 2D problem as a 1D problem. That is, we wanted to convert a two-dimensional system to a one-dimensional system. We know that a symmetric matrix contains redundancy. That is, elements aij will be same as aji. Thus, in this program, we propose to reduce the memory wastage, and at the same time we wanted to convert a two-dimensional problem into a one-dimensional problem. We would like to store the lower triangular portion of the matrix, symmetric matrix, into a one-dimensional array and propose how the elements can be accessed. Probably the user will be specifying the elements with respect to the 2D array, but however, the 2D array is stored as 1D array, thus the value will be accessed from the 1D array and then the value will be displayed. This involves conversion of the 2D problem to 1D problem, that is storing the 2D array into 1D array and storing the elements of the lower triangular portion only. This is also called as half vectorization. Probably you may be wondering why one should do all these things. The answer is to conserve memory. Also, to make the problem little simpler. Look, for example, a square matrix, the symmetric matrix is a square matrix. It contains n into n elements. Thus, we require n square locations, that is n square elements to store the symmetric matrix. We know that there is a redundancy. Ith row jth column element value will be same as jth row ith column element value. Why we should store the same thing more than once? Thus we propose to store only either a ith row jth column element or a jth row ith column element. Only one of them will be proposed to store in the memory. Thus there will be saving. If we plan to store the total square matrix, you require n square locations or memory elements. But if we propose to store only lower triangular portion, first row contains 1, second row contains 2 elements, third row contains 3 elements, the last row contains n elements. Thus, in total, we require how many elements? 1 plus 2 plus 3 plus dash 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 n. That is, we require n into n plus 1 by 2 elements only. That is a saving of almost 50%. For this purpose, we propose this type of methods. The program for this purpose is shown in the slide. Here a 2D array A is declared and a 1D array S is also declared. We wanted to store the lower triangular elements of the 2D array A in the 1D array S. First data is read into the 2D array. These two for loops are used to store only the lower triangular port of the 2D array A in the 1D array. In the following slides, we will demonstrate how the same thing can be done with our simulations. Once we assume that the 2D array low rectangular part is stored in the 1D array, obviously we will be interested to know how the user can access ith row jth column element from this 1D array. So for this we assume that user will be entering the row and column index ij. If I is less than or equal to j, which means that he is asking lower triangular element of the matrix. Otherwise he is asking upper triangular portion. So what we do is, if j greater than I, we will exchange I and j, because we know ith row jth column element is same as jth row ith column element, as the matrix is a symmetric matrix. So thus we will compare j with I. If j is greater than I, we will exchange I and j, and then we will calculate the index where will be the ith row jth column element of the given matrix in the 1D array. That is, k will be taken as I into I plus 1 by 2 plus j, and that will be printed by accessing the 1D array. Like this, the user will be still working at the 2D level, ith row jth column level, but our program accesses that element from the 1D array S, and it will be printed. Now let us try to simulate how really the 2D to 1D transformation takes place. How the lower triangular part of the matrix A will be stored in the 1D array S. Initially k value will be taken as 0, I is 0, and then inner for loop j will be starting, j value is 0. Thus the A00 element of the square matrix is stored in S0. A10 element will be stored in S1. A11 element will be stored in S2. A20 will be stored in S3. A21 will be stored in S4. A22 will be stored in S5. A30 will be stored in S6. A31 will be stored in S7. A32 will be stored in S8. A33 will be stored in S9. Like this. In the first row, one element A00. Second row, two elements 10, 11. Third row 20, 21, 22. Fourth row 30, 31, 32, 33. What are all these elements? Only lower triangular part elements of the symmetric matrix. They are saved into the 1D array. Like this, we have transformed, rather I say, the 2D array elements are now stored in the 1D array. Now let us assume that we are interested to access the elements of the 2D array really from the 1D array. That is, user may be entering the row and column index of the 2D array element, and we are interested to access the 1D array, read that value and display it. For example, let us consider user entered 3, 2. He wanted third row, second column element. we wanted to access from the 1D array. So to find out the where that 3 2 element will be located, simply we calculate 3 into 3 plus 1 by 2 plus 2, that is 8, which means that the element A32 is available in the 8th element of the array S. You can verify from the figure. Let us assume that user has entered 2 3, that is you wanted second row third column element value. However, we don't have really second row third column element value, rather its transpose mirror A32 is available. So what we shall do is we will exchange 2 3 as 3 2, and then we calculate 3 into 3 plus 1 by 2 plus j, that is 2. So we get again 8, which means that we don't have 2 3 element, but we have 3 2. As it is a symmetric matrix, 3 2 will be same as 2 3. Thus we write 3 2 element and print from the 1D array. As of now, we have explained how a symmetric matrix, it is a 2D representation, is converted into a 1D problem. This we call as a 1D representation of the 2D symmetric matrix. Let us assume that we require some operations like adding two symmetric matrices, subtracting symmetric matrices, multiplying two symmetric matrices, etc. We do not want to do in the 2D level, rather we wanted to do at the 1D level. That is, let us assume that we wanted to add two symmetric matrices whose 1D representations are available. Then we wanted the resultant symmetric matrix, its 1D representation we require. So this problem can be simply considered as adding the 1D array representation of the first matrix and the second matrix, just element by element adding only. We need not require to convert the 1D array to 2D array and then add in the 2D system, then again store in the 1D fashion, etc. Simply we know that two symmetric matrices, if we add, resultant is also symmetric matrix. Just simply we add the 1D representations of the both the matrices element by element. We assume the array A is a 1D representation of the first matrix, B is the 1D representation of the second matrix. Simply we wanted 1D representation of the addition matrix of these two matrices. Simply this can be achieved with the help of this for loop. Remember to do this one, both the symmetric matrices should be of same size. So we can add two 4x4 matrices. You cannot add a 4x4 matrix and a 5x5 matrix. It's not possible according to mathematics, not acceptable. So that we are assuming both the matrices are of same order. Their 1D representations are available in the two 1D arrays A and B. Thus we have written this for loop which will add element by element. Now we consider subtracting two symmetric matrices given their 1D representations. This also becomes a simple vector subtraction. Now let us consider how we can calculate the product of two symmetric matrices given their 1D representations. I am sure you will accept with me that product of two symmetric matrices is going to be symmetric. Thus, the product matrix 1D representation we are interested to find out. That is, we need to find out only the lower triangular portion elements of the product matrix. Those things we want to store in the 1D array fashion. In the following slides, we will demonstrate how one element of the product matrix will be calculated. That is, zeroth element if we wanted, then we require zeroth row of the first matrix has to be multiplied with zeroth column of the second matrix. Remember, both the matrices, they are in 1D fashion. They are represented in the 1D array. We have already explained how we can access ith row jth column element of any matrix from their 1D representations. Thus, we have written a function which takes the 1D representation of a symmetric matrix and ith row jth column element as arguments, and simply it returns the value of ith row jth column element of that matrix. This function will be used while calculating the product matrix. In the following slides, we will explain how zeroth row, zeroth column element of the product matrix, that is going to be the first element of the product matrix 1D representation. We will explain. We are using the function val, for which we are supposed to send the 1D representation of any 2D symmetric matrix and the size of the matrix n and the row index, column index, and this function returns the ith row jth column element of that 2D symmetric matrix by reading from the 1D representation of it. That we are using in the program. Let us assume that we want to multiply A00 with B00. That is the first matrix 0th row 0th column element with second matrix 0th row 0th column element. They are 4, 1. 4 into 1 is added to the resultant matrix first element. However, remember, these elements 4 and 1, they are not accessed from the 2D representations. They are read from the 1D arrays of the respective matrices itself. We have calculated zeroth row, zeroth column element of the resultant matrix, that is stored in the zeroth element of the 1D representation of the resultant matrix. You have remembered that we have taken the elements of the first row of the first matrix, and we have taken the elements of the first column of the second matrix. They are multiplied, and thus we have got 38. However, remember, while accessing the rows or row elements of the first matrix or column elements of the first matrix, really we have taken from their 1D representations only with the help of the function val. Like this, we can calculate the remaining elements of the product matrix or resultant matrix. Like this, we can convert a 2D problem into 1D problem. If we do so, we do require to identify methodologies to carry out the operations such as addition of two symmetric matrices, subtractions, multiplications, etc. That's also the essence of the data structures.